Alright, it's time to tackle these problems concerning a weak acid, strong base titration. I'll walk you through the first two parts A and B in this video. The problem is I am titrating 25 milliliters of 0.100 molar acetic acid, weak acid, with 0.200 molar of KOH, which is a strong base, and the Ka of the acetic acid is 1.8 times 10 to the minus 5. For letter A, nothing special. Okay, whether it's a weak acid or strong acid, this is the same process where we got to figure out the moles. We got to get to a situation where we have the moles of OH minus equals to the moles of H plus if the acetic acid is fully deprotonated. If the weak acid is fully deprotonated, so we move all the acidic protons. The weak acid is fully deprotonated. We got to get moles equals to moles. So we can definitely figure out the moles of acetic acid. 0.025. I'll quickly go to liters of acetic acid. We'll abbreviate this, I guess, AA. Times 0.100 moles per liter times. So here's where we set the conditions of equivalence, because we know that we need 1 mole of KOH to fully deprotonate 1 mole of the acetic acid of this molecule right there. Okay. So what do we have now? We have moles of KOH, and then we have the molarity of KOH. This is 1 liter on top and 0.200 moles. It's as simple as that. 0.0250 times 0.100 divided by 0.200. And that is liters, 0.0125 liters. And that will equal how many milliliters? 12.5 milliliters of NaOH, or KOH. And that makes sense because it is monoprotic, right? And for every KOH you do give up OH, 1 OH minus, and the concentration of the base is twice as strong as the concentration of the weak acid, and therefore you don't need 25 milliliters of the base, you only need 12.5, half of it. Okay. But you want to show your work, you want to prove that you could get by the calculations this condition here. Okay, now comes the kind of tricky part. That's your equivalence point, and we just figured out what volume is this point, 12.5. But now we got to figure out what is this pH. And in the previous video, we said it's not 7. It's actually going to be basic. It's going to be above 7, and I'll show you why. Think of it this way. Your equation is, in the Erlenmeyer flask, you have HC2H3O2 plus a strong base, KOH. And that goes to H2O plus C2H3O2 minus, the conjugate base. But at equivalence, all C2H3O2 is deprotonated. You remove that proton. Therefore, we have no C2H3O2, but all of it is now C2H3O2 minus the conjugate base. Now, this is an approximation, right? You do have maybe a little bit of acetic acid due to autoionization of the water. Okay, so, but this is a very good approximation that you imagine that all of this is gone. And you have all of this, and you actually know how much of this you have, right? Because you know how many moles of acetic acid you started with, and if all of that converted into the conjugate base, you know how much conjugate base you have. Now, why is that important? Because the conjugate base has an equilibrium with water. C2H3O2 minus plus H2O goes to, see, we get some of the acid back plus OH minus. We are doing an ice table, but not from the point of view of the acid, from the point of view of the conjugate base. Isn't that tricky? So you got to go back to your ice tables, and because we're figuring out for the conjugate base, we need actually the Kb. So there's a couple things going on here. We're going to do an ice, but we need Kb of the conjugate base. And also, we're going to solve for OH minus. Okay, so these are your tasks. And then we want the pH at the equivalence. So you know you could convert POH to pH. So you get POH, and then finally pH. 14 minus the POH equals pH. You want to set up the ice table first. Wow, there's one more twist, right? The twist is your new molarity is of a solution that is not that only, but also the added volume of base. Yikes. So we got to get, we're not ready, right? We're not ready to put in molarities for any of these because we don't know the new volume and we need the moles. So we're going to do an ice, but you know, to be able to do that, we need molarities because we have a new volume. Okay, so we're going to hold off on the ice and let's hit these one by one. So the first thing, the new volume. The new volume is 25.0 plus 12.5 milliliters, and that is 37.5. And you know we're going to change that into liters eventually to get molarity. That's a new volume. What is the moles of? Give me 1 second. Let me figure. Oh, we want the moles of that, the conjugate base. We know that the acid, this acid right here, was converted, all of it was converted to the conjugate base. So we need, if we can find the moles of this acid at the beginning, all of that was converted to that. So we have the moles of the conjugate base. That is what? That's literally the moles of this acid, because all of this acid was converted to the conjugate base when we added enough base, KOH, to change that into its conjugate base. Make sense? So we just need the moles of this. I'm not going to write it down. We know it's 0.025 times, yeah, that will give me moles, 0.100. Okay, that's how many moles So the moles is 0.0025 moles. So now we could get the molarity, the M, of C2H3O2. And that's going to go right here. Okay. And then we'll do the ice table. So it's these two numbers, 0.0025 moles divided by 0.37, oops, nope, 0.0375 liters. And the molarity now is 0.0667 molar. And that is, again, the molarity of the C2H3O2 minus. It's that number that's going to be put into the ice table. Now, since we said that all of this was converted into the conjugate base, this would be 0 for the initial. But obviously when we do the change in equilibrium, that will have a number, and that will have a number. And we solve for POH, and then pH. So this number is important. That goes into the ice. Goes to ICE, and particularly the initial. Okay. I need a new piece of paper, but we're almost done. Okay, we've done ice tables before. Yeah. Let me go ahead and do the ice table, and then we'll figure out KB after that. So we have that conjugate base. It's in water, right? We're establishing equilibrium with water. And we have C2H3O2H plus OH minus. And then our concentration for initially 0.0667 molar. Water doesn't matter. This starts at 0, this starts at 0. CE. You see how what we're doing? We're going to get the x's now. Minus x plus x plus x, x, 0.0667 minus x. We're going at it from the base point of view. See, we're not getting H3O plus, we're getting OH minus. So from the base point of view, we need KB. We are not given KB. We're given the Ka of the acid, and we could figure out the Kb of the conjugate base doing this equation. Remember, Ka equals Kb equals, sorry, Ka times Kb equals Kw. There's no temperature, but we assume if there's no temperature, let's assume it's 25 degrees. Kw is 1 times 10 to the minus 14. Okay, and I know I've belabored this point in the past, but if this is the Ka, which we have of the acetic acid, then the Kb that we're solving for is for its conjugate base, not for this molecule, right? We're not figuring out the Kb for this molecule. We need the Kb for this molecule, right? For this molecule right here. So anyway, we do have a Ka for the acetic acid times Kb equals 1.0 times 10 to the minus 14. Okay, 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Now, this is important because I feel like we're going to have to do the x is small approximation. 5.556 times 10 to the minus 10. Okay. Remember, we got to now put in these x's. So Kb equals x squared. Actually, let's put in the number, 5.556. We know the expression, right? Products over reactants. 5.556 times 10 to the minus 10, that's pretty small, divided by x squared divided by 0.0667 minus x. We're going to use the x is small approximation. And that way we avoid using the quadratic equation. Solve for x. Okay, good. Oops. I have that number stored, the KB, times 0.0667, square root of that. Get into scientific notation. So it's a small number. It's 6.087 times 10 to the minus 6. And what is x again? It's this one. It's the molarity. Molarity. Molarity equals the concentration of OH minus. Therefore, the POH equals log of that answer times -1, 5.22. And then therefore the pH equals 14 minus that. 8.78. Do you remember what this was? This is the pH at equivalence. The pH at equivalence. And we told you, or I told you in a previous video, that that number is not going to be 7. It's going to be slightly basic, 8.78. So here we have a pH of 8.78. So it's not, the solution is not neutral, but we did neutralize all of the acid. So do you see the difference between what is an equivalence point and what is neutral, pH 7? This is the equivalence point, but the solution is not neutral. Very interesting. It seems like a contradiction at first, but if you follow the math, it's true and it works out in the lab also. Your titration will have a pH greater than 7 at the inflection point. I think that's all I need to say. Okay, this is what I wanted to do. So for question A, for problem A, what is the equivalence volume? The key is what? Is just figure out the moles of base to neutralize all the acid. And then obviously get the volume. It doesn't matter if it's a strong acid or weak acid. For part B, so part B is the tricky one, right? The key to finding the pH at equivalence is know that all the HA has turned into A minus, and then do an ice for A minus, right? A minus is the conjugate base. So your ice table is going to look like this. A minus plus H2O goes to HA plus OH minus. And then when you have ICE, it's this number that you want to solve for POH, and then you get to pH. Okay, and don't forget, because you're using the base, the conjugate base, you need KB, and typically you're going to have to solve for that. Need to solve for KB. That is A and B, and those are your tips. Okay, remember those when you come across problems like that. Okay, in the next video, these are not as complicated. Okay, these are not as complicated as what we just did. So I think I could fit all three, C, D, and E, in one video.